Hi guys, welcome back to Ryan Study Corner. I am Ryan and the aim here is to make learning as fun, easy and accessible as possible. Now, today we are going to be learning about scalar and vector quantities. The words scalar and vector may seem a little bit foreign, or you may remember vector from vectors in maths. It's similar. Now, even if they seem a little bit foreign, think about the entire title, the last word of the entire title, scalar and vector quantities. Now, if we think way back to our first video, we said that a quantity is anything that you can measure and that is denoted by a number and sometimes with a unit. We covered things like mass, length, temperature, density, all of these things. And now we're going to take it one step further to put these into two categories, scalar quantities and vector quantities. Now, before you start this topic, you have to ensure that you have a really good grasp on two topics, Pythagoras Theorem and trigonometry. I'll link two videos in the description box below, so check those out. When you feel like you're really comfortable with them, then come back to this video and start working on scalar and vector quantities. So let's get started. Right, so as I said, the first thing we're really going to think about is what is this word at the end of this here, scalar and vector quantities. What is a quantity? A few videos ago we talked about how a quantity is anything that you measure and is denoted by a number and usually by a unit as well. Now this includes things like density, mass, temperature, volume, relative density, all of these different things. Now, what we're going to do is group these into two categories, scalar and vector categories, or scalar and vector quantities, and see how we interact with these. Now, at the end of this video, you should be able to say that I can differentiate between a scalar and a vector. I can give examples of scalar quantities, I can give examples of vector quantities, I can calculate the resultant of vectors, and I can resolve a vector into its horizontal and vertical components. Now, by definition, a scalar quantity is a quantity that has magnitude but no direction. So it's just the size. That's what magnitude refers to. This includes things like distance, mass, speed, and all of these quantities we see listed under that. Now, a vector quantity is a quantity that has both magnitude and direction. And these include all of these underneath here, including displacement, velocity, weight, all of these things. Meaning they both have magnitude, as in a size that we show by using whatever number it is, but only vector quantities have direction. Now, if we think about it, if we look at displacement versus distance, you might think, what really is the difference between this? They're both essentially distance. But if you think of it this way, imagine you're at a kiosk in the mall. So we're at this kiosk here, and I'm at the kiosk and you have to meet me, or I'm near to the kiosk rather, and I tell you, okay, I'm 100 meters away from the kiosk, so that you could know where to find me. That 100 meters, you don't know if I'm referring to in this direction, in this direction, this direction, this direction. It could be any number of directions, because what I told you is really the magnitude. I only told you that it's 100 meters away from the kiosk, but we don't know what direction that 100 meters is in, compared to displacement, which refers to distance in a particular direction. So if when I'm at the kiosk now, I say I am 100 meters east of the kiosk, then we know I'm 100 meters in this direction. So it's the same magnitude of 100 meters, but now we have a direction. The same thing comes into play for speed. You may think speed and velocity are exactly the same thing because, to be honest, we use them interchangeably in everyday life. But speed tells us how fast something is going, the distance it's covering in a certain amount of time. But it doesn't tell us the direction. So I could say I'm driving at 100 kilometers per hour. But you don't know if I'm heading east, if I'm heading west, north, south, where I'm heading. But if I say I am driving at 100 kilometers per hour westbound to Port of Spain, then you have a direction. So we have the same magnitude in both instances. It's just with displacement and velocity, we have the direction. Compared to something like mass is just the amount of matter something contains. We don't say that this bag is 1 kilogram of potatoes salt. That doesn't make any sense. That's not how we speak, because mass doesn't have a direction. It's just a magnitude. And you may think that the corresponding thing I have here on this table is weight. You may think, but weight is the same thing. But no, weight is a force as a result of acceleration due to gravity. So weight is pulling us down to the earth. So we have a direction. Weight will always act downwards or towards the earth. So we see it's the same quantities that we're used to. It's the same numbers that we're used to dealing with. We just have to understand that once direction is involved, it means it's a vector quantity. So a scalar quantity is a quantity that has magnitude but no direction, and a vector quantity is a quantity that has both magnitude and direction. Now, how do we add scalar quantities? If we think of it, if I have let me make this a bit smaller up here. If I have a parcel of potatoes that is 2 kilograms, and I have another one that's 5 kilograms, then my resulting or my total mass is just 2 kilograms plus 5 kilograms, and that gives us 7 kilograms. But with vectors, we have an additional step, because what we just did there with adding the masses is really just added magnitude, because we have no direction with masses. But with vectors, direction comes into play. So let's look now at how we combine vectors. Our first example here is how do we combine parallel vectors. We know what parallel means in the general sense. It's two lines that won't ever meet and they're the same distance apart. And what we're referring to in this case is vectors that are acting in the same direction. So if we look at these two guys here, let's say you buy a couch from Standards and they're bringing that couch into your house. They are both walking towards your house. The guy in front is moving it with a force of 20 newtons, and the guy holding the back of the couch is moving it with a force of 25 newtons. Now, what is the net force or resultant force that both of them are lifting this couch and moving it with? They are in the same direction, so all we have to do is add them. So that's how we have 25 newtons plus 20 newtons, and we get 45 newtons to the right. note that we make sure to mention the direction. Now, what about when they aren't acting in the same direction? What do we do then? If they aren't acting in the same direction, it's very similar, but we add that additional step of factoring in the direction. We do this by expressing one as positive and the other as negative, because a question may say one is moving to the left and one is moving to the right, or one is moving to the north and one is moving to the south. But with our numbers, we have to find a way to show this opposite direction. So what we do is we write a negative sign in front of the opposite one. So we would call one positive. In this case, let's say the first one that I'm seeing is 400 newtons. So the force that is moving opposite to that, I would put that as being a negative number. So then it comes like we're adding directed numbers. So if I put the opposite one as negative, so I would have now 400 newtons, since that's the one I put as positive, and I put the opposite direction as negative. And we always add all of the forces. So we're adding, but we're putting this negative sign in front of the 300. Now remember, this negative sign only means that it's acting in the direction that's opposite to the first quantity. So because that the children on that side who are pulling with a force of 300 newtons, because they are pulling in the opposite direction to the kids who are pulling with a force of 400 newtons, that is the only reason we have this negative sign here. And we know from basic math that a plus and a minus next to each other is the same as a minus. So then we have 400 minus 300, and that gives us positive 100 newtons. This positive 100 newtons means that the resultant force will be moving in the direction of the force or the vector that we hadn't put as the positive one, which is the 400. So it means that the guys on that side will win first of all, which we knew just by looking at it, but they'll pull off in this direction, they'll pull everyone in that direction with a force of 100 newtons, which we could already kind of see intuitively just from looking at the fact that one is 400 and the other is 300. Now, you may be wondering, will I get it wrong if I put the 400 as negative and the 300 as positive? And the answer is no, and here's why. Remember, the negative does not change anything with it, with the problem. It just shows us the direction. So if now, let me erase this, and I put this side as negative and this side as positive, then it means we add as usual. So we'll be adding negative 400 plus 300. What does that give us? That gives us negative 100 newtons. But remember, this isn't actually negative in the traditional sense. This means that the direction of the resultant force will be the same as the one that we chose to be negative. And since we chose this one to be negative, it means we'll be moving off with a force of 100 newtons in that direction. So you see, regardless of which we put as negative and which we put as positive, you'll get exactly the same answer, as long as we remember that all this negative sign shows us is the direction of the force. Now, more likely than not, you are probably going to stick to the norm, which is that any vector moving to the right is denoted as positive and to the left is negative. So you can do it like that if you like, I know a lot of students like to do it like that because with most things in our lives, if you think about it, we usually choose the left as negative. So because that's clearer in your mind, you can run with that because it really doesn't make a difference. It's really whatever floats your boat. So let's try some other examples. If we look here, we see 10 newtons in this direction and 10 newtons in this direction. So since it's the same direction, it's going to be 10 newtons plus 20 newtons, and that gives us 30 newtons. Now for B, the forces are acting in opposite directions. So let's say we choose right as positive and left as negative. We're adding as usual. This means we're adding negative 20 plus 40. And that gives us 20 newtons. This means that the trolley will end up going in the direction of whichever force we put as positive, which we see is true here. It's moving off with a magnitude of 20 newtons in the same direction as the 40 newton force. Now finally, for part C, we have 25 newtons acting to the left and 25 newtons acting to the right. So let's use our same type of guiding principles that we just used. We go with right as positive and left as negative. We're going to add, as usual, we're adding everything. So we're adding negative 25 newtons plus 25 newtons. That gives us 0 newtons. So we have a resultant of 0. So this is the way that we will always add parallel or anti-parallel vectors. Now, what do we do when we have both parallel and anti-parallel vectors? Let's try an example and see. So here we have 2 vectors acting in one direction and 1 vector acting in the opposite direction. So what I'm going to do is I'm going to work out the 2 that are acting in this direction first. So I'll say we have 1.5 newtons plus 2 newtons. They're acting in the same direction, so it doesn't make a difference with signs because it'll be the same sign anyway. So this gives us 3.5 newtons. So if we redraw this underneath, it means we have 3 newtons in this direction and 3.5 newtons in this direction. Just as we did before, I'm going to put to the right as positive and to the left as negative. And now we're going to add all of the vectors around this point. So we'll have negative 3.5 newtons plus 3 newtons. And that will give us negative 0.5 newtons. This means that this box will move off with a force of negative 0.5 newtons in the direction of the negative force, which is this way or to the left. And it's as simple as that. Now, sometimes rather than pulling directly in the direction that we have to go in, we can pull something at an angle. And what does pulling it at an angle cause? It gets the body to move in the direction that we want it, because if we look at this, it's still going to move straight forward this way. It's just they are pulling at an angle to get the same resultant force. We're going to try a few examples with it in just a bit. But if we look at it, we see they're both pulling at an angle, and it will get the trolley to move forward on the ramp. Here we have another example. If two people are holding a bucket, they're holding it at an angle, they're not holding it straight up, but the resultant motion of the bucket would be straight upwards. And then we see it all the time as well with tugboats and cargo ships. We'll have two tugboats and they'll be pulling at whatever angle, and the tugboat, or the cargo ship rather, would still move forward or in whatever general direction they want it to move. Let's look at some examples. The angle that the vectors are acting at here is at a 90-degree angle. It says Andy had to walk around the construction site on his way home from school. The path that he took can be seen below. What was his resultant displacement and what direction was this from his horizontal path? So they already gave us two sides. And they're asking us what was his resultant displacement and in what direction was this from his horizontal path. They're giving us the length of one side, or one part of his path home, and they're giving us the other path once he bends the corner. And we notice that our units are meters, but this meters is not distance, it's displacement. So what do? I am going to draw the resultant, which, if you think about it, if he walked this way and then walked up, I like to think of it as you're walking around a field, but the shortened form of it, or the shortened distance, would have just been if you had walked diagonally like that. So that is where our resultants will be. So that's our resultant. And when they say what direction it is from his horizontal path, they mean that in terms of what size angle of rotation did he have from his horizontal path to the resultant. So this is where Pythagoras Theorem and Trigs is coming in. So we have the length of two sides. We need to find the resultant, which in this case is the hypotenuse, and they also want us to find that angle. So let's use some of the Pythagoras Theorem skills and trig skills that we just reinforced before we watch this video. If we look at it, we can call this A, B, and C. And we could use Pythagoras theorem that says A squared plus B squared is equal to C squared. Now A squared here would be 30 squared. B squared is 40 squared, and that would be equal to C squared. 30 squared is 900, and 40 squared, 4 4s are 16, so 1600. Now C would be equal to the square root of these two things added. So that gives us the square root of 2500 is what we get as C. I personally like to see C on the other side, but it doesn't make a difference. That doesn't change the information here anyway. It's still just C is equal to the square root of 2500. And if we think about it, square root of 2500 is 50. So therefore the length of the resultant is 50 meters. So that is his displacement. Now we still have to find the direction from his horizontal path, and remember that just means what is the angle between the horizontal path and the resultant. So if we look at this, we have this angle here, and if we think about trigs, the side that is opposite the angle is what we call opposite. The side that is along the angle is what we call adjacent, And well, the resultant we know is the longest side and it's opposite the right angle, so that's the hypotenuse. Now if we want to find theta, let's use the information that they gave us, if possible, to find it. So I'm going to use 30 meters and 40 meters. So that means I'm going to be using the opposite side and the adjacent side. So now I think if I have adjacent and I have opposite, and I know my trig functions, SOHCAHTOA, so sine is opposite over hypotenuse. I know cosine is adjacent over hypotenuse, and I know tan or tangent theta is opposite over adjacent. So I realize, hey, tan has both opposite and adjacent. So that means I can say tan theta is equal to opposite over adjacent, which means tan theta is equal to 40 over 30. Now you can do one out of two things. You can leave this as a fraction and rearrange, or you can convert it as a decimal. Just for those people who like to work out everything at each step of the way, I'm going to convert it to a decimal. So this will be equal to 1.33. Now if we want to find for theta, we know we have to have theta alone on one side and we have to put that tan over on the other side. When tan goes over to the other side, it becomes tan inverse of what we just found. Or if you felt like leaving it as a fraction, tan inverse of 40 over 30. This will give us an angle of 53.13 degrees. So we've found the magnitude of the resultant, that is 50 meters, that is his resultant displacement. We've found the angle that resultant is away from the horizontal. So it wasn't stated in cardinal points, east, west, north, or south. It was given as a degree from the horizontal. Now usually they ask you to do it from the horizontal, but sometimes they ask you to do it from the vertical as well. Now if they don't explicitly say, hey, find the direction from the horizontal or from the vertical, I usually just go with from the horizontal, but it doesn't make a difference which one you choose. You just have to make sure to say 53.13 degrees from the horizontal or the vertical or whatever side you chose in this particular question. So we've just calculated the resultant and the direction if they've given us the two initial vectors and we have to combine that to find the resultant. But sometimes we are given questions where we already know the resultant and we know the length of one side, and we have to manipulate this that we just did here to make the one of the original vectors the subject of the formula. So rather than finding for the resultant, we're trying to find one of the original vectors that we would have had to add in order to create that resultant vector. So it's very similar to what we just did here. There's only one tiny tweak. So let's look at an example like that. So here we have that Jaden pushed a trolley around a corner with a force as seen below. If the resultant force was 40 newtons, what was the force used to head west around the corner? And what direction was the resultant force from the horizontal? So what they're saying is that we know that he went this way and then this way. But we know that he pushed this way with a force of 20 newtons, but we don't know what the force that he applied on this side is. But we do know that the resultant is 40 newtons. So rather than having to find the resultant like we did before, now we have to find a missing side. But here's the thing, the process is still exactly the same, because I'm going to use Pythagoras Theorem just as I used before. So if I label each side as something, let's say I label here A, I label here B, and I label here C, then I can use Pythagoras theorem and say that A squared plus B squared is equal to C squared. But in this case, I want to know what A is. So therefore, I want A squared on one side by itself. The other thing that is on the same side of A squared is B squared. So I have to think now, what can I do with this B squared to get it over on the other side? Now if I look at it, I see on this side we have plus B squared. So if I carry it over on the other side, it will become negative. So I'll have A squared is equal to C squared minus B squared. So if I plug my values in, C squared is 40 squared and B squared is 20 squared. So we'll have A squared is equal to 40 squared gives us 1600. 20 squared gives us 400. So A squared is equal to 1200. Now if we want to find for A, that means we'll have to take the square root of everything, so that we'll have A is equal to the root of 1200. Now if I plug that into my calculator, so I'm just plugging that in here, I get the root of 1200 gives me 34.64. So that means 34.64 newtons. So the force that he pushed the trolley with over here is 34.64 newtons. So we have our missing side. Now the next part asks us to find the direction of the resultant from the horizontal. Now what you could do here is say, well, let's take this angle because we want to see from the horizontal. So what was the angle between the horizontal and the resultant? So we have some tricks to use now. Because first things first, if we think about it, we know that vectors, it really doesn't matter what their spatial arrangement is, because we could get it to be from one particular point. So if we have this here, and we know that this side is 40 newtons, because it's literally going to be like the image of this, we could also say that this side here would be 20 newtons, and then the base here would be 34.64 newtons. So therefore we could use our tricks like usual and figure out what that angle is. Now usually I would always say to use the values that they have given us, because we know in case we made a mistake somewhere here, that will throw off the value for this. And if we use this to calculate the next step, then it means that part as well would always also be thrown off. But this time I'm going to do that because I want to stick with tan, only because I know most students are very used to using tan and prefer to stick with tan in instances like this rather than trying to figure out what sine or cosine is. But keep in mind, you have to know all of them inside out for maths anyway. So if you're good with that, proceed and choose the one that makes the most sense using the sides that they've given us, but I'll just use tan just this once. So if I look at this triangle now and we want to figure out what theta is here, then here is my opposite side because it's opposite the angle, and here is my adjacent side. So I'm going to use tan theta is equal to opposite over adjacent. So therefore tan theta is 20 over 34.64. So 20 over 34.64 in my calculator gives me tan theta is equal to 0.577. But we want to find for theta, so we need to send this tan over on the other side. But when we send it over to the other side, it doesn't remain as tan, it becomes tan inverse of this. And if I punch that into my calculator, I get 30 degrees. So it means that this angle here is 30 degrees. 30 degrees from the horizontal. But we know we could have used sine because we could have said opposite over hypotenuse and we would have gotten the same answer. So feel free to try it with sine as well. You should get the same answer unless I made a mistake here or you made a mistake with your sine. So try it out. Now we've just looked at how we combine vectors when they're at an angle, but we only dealt with vectors that interact with each other at a right angle. But very often vectors would interact with each other at, or they would be less than 90 degrees or more than 90 degrees separate or apart from each other. So the method we use to work this out now is the parallelogram law, because remember we can think of vectors as arrows kind of just floating around in space. And if you look at the vectors A and B here, as long as the length remains the same and the direction it's pointing remains the same, then it would be exactly the same even if I move A over here. As long as the length is exactly the same and it's parallel to that A, meaning the direction is the same, it is the same vector, so I can move this around anywhere. And the same thing goes for B. I could move B to down here because as long as it is parallel, so it's pointing in the same direction and it has the same length, we could move it around. So what we do is we move the two vectors around to come from a common origin. And then we build a parallelogram around it, which we can use to figure out the angle, to find direction, and the size of the vector. Now, I can't really do that properly here because we need our compass and protractor for it. So what I'll do is I'll link a video below, and you can use that. It's a really nice video. Just beware. The audio sounds like if it's one of those Nicki Swift videos, so just be mindful of that. But it explains it really, really well. I like to use that video. So check the video out and try combining vectors using the parallelogram law. So for this entire video, all that we've been doing is combining vectors. We combine some scalars too at the beginning, but for the most part, combining vectors. Now, what about if we have the resultant, but we don't know what the two other vectors were that were added up to find that? So what if we have to work backwards now and we're like, hey, this is the resultant vector. What are the two vectors that we would have added to get this? What we call that is resolving a vector. And resolving a vector refers to separating a vector or resultant vector into two components, meaning a vertical component and a horizontal component, which would have been the original vectors that we combined to get that. So to calculate the horizontal component or the horizontal vector that we would have had initially, we take the magnitude of the resultant. In this case here we're using f, multiply that by cosine theta, theta being the angle from the horizontal. Now to find the vertical component or the vertical vector that we would have used initially to get this resultant, we use f sine theta. F is still the resultant and theta is the angle. We can take this at face value and literally just plug our resultant into that and our angle into that to find for the other sides. But before we do that, I still just want to go through how we ended up with those formulas so that it makes a bit of sense in our mind as we're going through it. So we're back to trigs. If this is theta, then the angle opposite to that is our opposite side. So I'll name here opposite, and I'll name here adjacent because it's alongside the angle, and we know our hypotenuse. So if we want to find the value of the opposite side, and the only information we have up front is the hypotenuse, then it means we can use sine theta is equal to opposite over hypotenuse. So sine theta is equal to opposite. In this case we'd call it, I'm going to put VC as vertical component for short, over hypotenuse, and the hypotenuse is our resultant, which in this case is f. Now if we rearrange to find out what the vertical component is, we'll say, okay, I have that f there, but I want the vertical component by itself. So what do I have to do to get rid of that f underneath there? We always tackle low-hanging fruit first, we know that. So we send our f across, and on this side it was this divided by f, so when it comes on the other side it will become multiplication, and we'll have f sine theta is equal to the vertical component, which is literally what we have here. Now for the vertical component, or the horizontal component, sorry. The horizontal component is adjacent, and the only information we have is the hypotenuse or the resultant. So adjacent and hypotenuse, which trig ratio has, oops, I'm starting to put SI, which trig ratio has adjacent and hypotenuse? Cosine theta, and that is adjacent over hypotenuse. Let's plug what we know in. Why do I keep writing sine? Cosine theta is equal to adjacent here. I'm going to put HC for horizontal component, and the hypotenuse is our resultant, or f. Now same thing again, we want the horizontal component on one side, so we need to get rid of this f. And if on this side it's division, it will become multiplication on the other side. So then we'll have f cosine theta is equal to our horizontal component, which is the same thing we have here. Now, do you have to know by heart for this level how to derive this? No, you do not. I just wanted to explain how we get this formula so that it makes sense going forward. But you can just learn off vertical component is equal to f sine theta, and horizontal component is equal to f cosine theta. So keeping these formulas, these two formulas in the back of our mind, let's try some examples. In this question, what we're going to do is we have this trolley being pulled along a track, and we see that the force in this direction is 400 newtons. What we need to find now is what is the force that's acting in this direction. So we're going to resolve this force into this direction. So we're trying to find the horizontal component of this force. And we see here they've given us the angle as 60 degrees. So let me just draw this. We have this as the resultant, which is 400 newtons. And we have the horizontal here, and theta is this here, which is 60 degrees. So we just derived the formula, so all I'm going to do now is use that formula. And for the horizontal component, which I'm just going to write 8C4, horizontal component is F cosine theta. F in this case is 400 newtons. Cosine theta is 60 degrees. So if I plug that into my calculator now, 400 cosine, put my 60 in brackets, that gives me 200 newtons. So it means the horizontal component is 200 newtons. And that's the answer. Very, very simple. In this question, they didn't ask for the vertical component, so it's just one. Now let's try another example. Here we have Cindy, who throws a ball with a velocity of 20 meters per second at an angle of 50 degrees. Calculate the vertical and horizontal components of this throw. So let's draw a little triangle because it just makes it easier. So the velocity that Cindy throws the ball with is here, and that's the resultant. I'm just putting F, but really let me put R just to switch things up, plus I prefer to see R as the resultant anyway. And our angle here is 50 degrees, and they want us to find the vertical component and the horizontal component. So we just use our formulas again. Vertical component is equal to, I'll put R in this case, R sine theta, or you could put F sine theta, it really is up to you. So the resultant is 20 sine 50. So if I plug this into my calculator, what do I get? I get 15.32 meters per second. So it means the horizontal component, or the original horizontal vector that would have created this resultant, is 15.32 meters per second. I'm going to use the same formula for the horizontal component. I feel like I was saying horizontal component all the time. I meant vertical component. I hope you all picked up on that. So horizontal component, we use our cosine theta. Or if you prefer to think of it as F, since that's how we derived it, then you can use F sine theta. F cosine theta. What's going on with me today? My resultant is 20 cosine of 50 degrees. So let me plug this into my trusty calculator here and see what it gives me. It gives me 12.86 meters per second, which means that the horizontal component, or the horizontal vector, which would have created this resultant, is 12.86 meters per second. So that brings us to the end of today's video. We've looked at what is a scalar and what is a vector quantity. We said that a scalar quantity is a quantity that has magnitude only, and a vector quantity has magnitude and direction. We showed how we add scalars, which is just how we add everything in everyday life, and we looked at how we added vectors. And we said that when adding vectors, the direction comes into play, and we use a negative sign to show opposite direction. We used Pythagoras Theorem and trigonometry to find out what was the resultant, or to add the vectors when they were acting at an angle to each other. We just touched on it, and there's a video in the description box of how to use the parallelogram law to find the resultant and the direction, that is the angle, remember that. And finally, we resolved a vector, which means separating a resultant into the two original vectors that would have created it in the first place. So I hope you all understand everything that we did here. So remember to stay safe, guys, and be kind to yourselves. Bye bye, see you in the next video.